relevant to what you might see on today's test. Okay, so let me just do that. So what I'm going to do is let me now get and open up a file here. So file is going to be now this. Yeah. By the way, on today's test, there will be no rational inequality. So like example 12 and 13, I did not put that, and I did not give you any problem on absolute value yet. Okay, so absolute value, but there will be problems where you have to solve an equation, and factoring those things are needed on today's test. Okay, so now what I would like to do is let me move on to section 7.1. So let me do that. So let me open up the file. Let's see, asymptotes. No, let's skip the asymptotes. Let me now open up the file. Name the number 0711 functions. Oh, actually, this is actually related to what you will have on today's test. Okay. So here, you know what functions? Definition, a function, and a relation. What are all these here? I'll just let you read this. You have heard this term function so many times. So, okay, let me just quickly go over the definition here. The definition, a relation is a correspondence between two sets of numbers usually, where each element in one set corresponds to one or more elements in another set. That's called a relation. And then a function, right underneath example 3. A function is a correspondence or rule from one set to another set where each element in one set, the first set, corresponds to exactly one element in B, one element in the other set. The first set A is usually called a domain, and set B is commonly called range, although anyway, just call it range. Okay, so anyway, in advanced math they actually call this codomain. Okay, but anyway, range is okay. But anyway, as long as you understand this, okay, so okay, that's fine. Okay, I'm not going to spend too much time on this one. So how about, let's say, for example, how about example 6? Is that a function? Let's see. Okay, let's look at example 6 here. Sorry. Why did I click that? Am I sharing this page here? 1 second. Sharing this. Yes. Back to section 1.1. Okay, let's look at example 6. Example 6. Let f be a function from the set of rectangles to the set of R plus, which is a set of positive real numbers. R plus, what I mean by R plus is set of positive real numbers, all numbers which are bigger than 0. So a function is a correspondence from one set to another set. The first set is the set of rectangles. This is not the set of numbers, it's a set of rectangles. And then the range, the second set, or sometimes called the target set, is a set of real numbers. So here we have a rectangle. So on the first set, we have a bunch of rectangles. Then we have a rectangle here. Rectangle here. Then we have all these rectangles here. And then from this set, we match all the real numbers. Real numbers like 1 over 10, or 2, or 6, or 12, and then 12.1, all numbers. Okay? So this is what we mean by R plus. So we can call this by R plus. That's a set. That's the set B. We can set that to be B. And this one, we'll call it A. That's the domain. And this A happens to be the set of rectangles. Okay, this A right here happens to be the set of rectangles. So let me write that down. How about this? I can write that. Set of rectangles. Okay, so now set of rectangles. So the first set, or the domain, is a set of rectangles, and B is a set of range. That's a set of positive numbers. Now we want to make a correspondence. You want to create a function. So when you create a function, we have to create a rule. A function is basically a rule. So what is the rule here? The rule is this: where, and there's the rule. A function f of the rectangle. So if you put in when you put in a rectangle into this function, what do you get? We will get the area of the rectangle. So that's what that is. So if you put a rectangle like this, let's say this guy is 2, and this guy is how about 6? If this is 2 by 6, then we are going to match this rectangle 2, and then let's make a correspondence. And the correspondence will be, we are going to match this to this guy right here. We match this to 12. And then this guy is, how about 1 and 2. So we are going to match this guy to 2, because that's the area. So here we are setting up a rule.
Hi, darling.
So if you have let f of a rectangle, if the input is a rectangle, then what is the rule here? We are going to match that we are going to make a correspondence to the area of the rectangle.
Hi, sweetie.
So that's how we match. So for this input, let's say this guy is, how about square of 2? And then let's say square of 2. This guy is also a rectangle here in the domain. And so for this rectangle, it's actually square. But square is a rectangle. Square is a special rectangle. So square of 2 by square of 2, that will match to square of 2. So to 2, because that's the area. And then for each rectangle, we will make a correspondence to a number which represents the area of the rectangle. So the question is that a function? Is that a function? Is everybody with me here? Example 6. For each rectangle, we will match that to the area of the rectangle. So the function f of the rectangle is equal to now the area. So for each rectangle in the domain, we are now going to match the area of the rectangle in the range. Okay? So is that a function?
No.
Yes.
Yes.
Is that a function? Yeah, by the way, the domain is not the set of numbers, it's actually a set of rectangles. So the domain in the range could be sets, they can be any sets, although in math, we do consider the most common sets we include are, of course, the set of numbers. But it does not be set of numbers. It could be set of rectangles, set of circles, a set of countries, set of states. It could be anything. Set of people, or whatever. It could be set of things. It could be anything. But the most common set we encounter in math is a set of numbers. Now the question is, how do we match it? For each element, that is each member in the set A, do we have exactly one item matched in set B, which is called the range? If we have if everybody in A matches exactly one element in B, that's what we call a function. So this rectangle only matches to number 12. Yeah, that's 12, because this rectangle's area is 12. The area is only 12. The area is not 11 or 10. There's only one area. So that's 12. So that is, what is this? So again, question, going back to the original question, is that a function, class?
Yes.
Yes, it is a function. And the answer is yes. Of course, I can create another function. I can create another function where the input is a rectangle, and then match that, and then make the correspondence to the perimeter of the rectangle. If I do that, that becomes another I can create a function like this, G, a rectangle, is equal to the perimeter of the rectangle, If I do that, that becomes a different function. If I match for every rectangle to the perimeter of the rectangle, that will also be a function too. That will be a different function, because every rectangle is only one perimeter. There's only one perimeter. A rectangle cannot have two perimeters. There's only one perimeter. So that will be a different function. So the rule is actually called a function. So in order to have a function, we need to have two sets, where the first set is called the domain, and the second set is called the range. And then most importantly, we need to have a matching correspondence, a one-way correspondence. A one-way correspondence. It's like matching, but it's a one-way matching. One-way matching. A one-way correspondence. That is a one-way rule. And if you have that, then that's called. And then for each element in the domain matches to exactly what element in the range. That's called a function. If you have any kind of matches, then we call that a relation. Okay, I can spend the whole time on relation, but again, you know what? Please look up what a relation is. In fact, you have to know what a relation is before you understand what a function is, okay? But now let's look at example 7. Example 7, let's try to do this one. Example 7. Example 7. Now, example 7 is it's a relation f from R plus two rectangles. Oh, this one is different. In this case, the domain is a set of positive numbers, and then the range is a set of rectangles. Now, how do you match this? Okay, well, what is this? F of x is equal to the rectangle whose area is x. Oh, I see. So in example 7, let's make a match here. Example 7, what is the relation we are talking about? The relation here is this one, and we have this. In this case, what is let me just call this guy A, and this guy B. A is the domain, and B is the range. So A in this case is R plus. Positive real numbers, all the numbers which are bigger than 0. R plus in interval notation would be called is equal to all the numbers from 0 to infinity. That will be called, that is the interval notation. All the numbers, or we can say this, x, where x is positive. Positive like this. This is the way how that's R plus. R plus is set of all the numbers which are positive. Positive means it cannot be 0. Okay, positive. This, okay, R. Okay, anyway, it's kind of messy there, but then R plus. And then, so here we have a bunch of numbers like 6. Let's have a 2, and there's 6. And then there's what? I don't know. Well, I don't know. There's 25. Then there's what? 100. All numbers. And then here we have, let's say we have a rectangle like this. 1, 2. 1, 2. And here is we have another rectangle like this. How about this one is, let's say 2 on this side and 3 on this side. So we make a correspondence, a one-way correspondence. A class, is that a function or not? The relation example 7, is that a function or is that not a function?
Yes.
Is that a function? Now you have to understand the rule here carefully. It says here if the input is a rectangle, and if the input is a positive number, then what's the output? The number we put in, or the number, or the element in the first step, that's called the input, and then the element in set B, or the element in the range, that's called the output. Input, output, input, output. Okay, element in the domain is called the input, and the element in the range is called the output. So in this case, the input is R plus, then the output is a rectangle whose area is X, whose area is the input. Okay, so 2 here, then that can be mapped to that can be correspond to a rectangle which is 1 by 2. Now 6 is a number, then 6 can be mapped to what? The 2 by 3. But this is actually not a function. Why? Because we have a 6 here. There's another rectangle right here, which is what? 1 by 6. And this guy can also be mapped to this guy right here. Oh. And then there's another rectangle like this guy. How about square of 6 by square of 6? It's actually a square, but that's a rectangle too. So this 6 right here can also be mapped to this rectangle right here. So note that in this case, if the input is 6, how many outputs are possible here? If the input is 6, the question is how many outputs, how many rectangles have area 6? Area equal to 6.
3.
How many rectangles we have with area 6?
3 rectangles.
3? Just 3? Yeah, I wrote 3. I drew 3 here. But do you have just 3 or do you have more than 3? By the way, we allow decimals too. So it could be like this. It could be a very skinny rectangle right here, where this side is 60, and this side is 0.1. Okay, so I cannot, of course, that's not 0.1, but anyway, we can have a rectangle where the sides are like this, a 60 by 0.1. So let me write that rectangle here. How about this? Let me draw this rectangle right here. And draw a rectangle like this, a real skinny rectangle like this. A real skinny rectangle where this side is 60, this side is 60, and the short side is 0.1. What is the area of this skinny rectangle? What is the area of the skinny rectangle here? Also 6. So we also have that rectangle too. So the question is, if the input is 6, then we have to match that to a rectangle, make it one-way correspond to a rectangle whose area is 6. But then the question is, how many rectangles have area equal to 6? Oh, there are tons of it. And there are zillions of rectangles. The zillions. The infinite number of rectangles whose area is 6. And therefore, as you can see, in this case, the relation we see right here is not a function. The answer is no. I don't know. Everybody, do you follow me here?
So if a function
Yes.
has infinite results, it is not a function by definition.
Right. So the definition of the function is basically this here. Yeah, I can go back here. You know what? Let me say this. Okay, so this one here. Let me save this, and I'm going to clear this. If I go back through this here, it's a function. It says here a function. A function is a correspondence or a rule from one set A to another set B, where each element in set A, or the input, corresponds to exactly one element in B. That's the key. So if you look at this definition of function, is this guy right here. It's exactly one element in B. That makes it a function. If we do not have that condition, then it becomes that becomes a relation. Relation is like this. Let's say this is our math class. Let's say this is a class, and this is all and then this is here over here. Let's say let's say here, let me say, how about this is, let's say, California. So let me call this is A, is equal to, and let me say, how about this? How about, let's say this. How about this? This is, let's say, people who live, people in California. And then how about, let's say part B, or not, which is a good state? Somebody tell me, can you name me a good state? What is your favorite state here? Wait. Okay. Let's say people in what? People in, how about Washington? It's like this. So let's say California is a California state, and Washington is Washington state, and let's say A is the people in, all the people in California. So let me put a mark here. So these are the people in California, and then all of these people are, they kind of look like two potatoes, right? Don't they? Are they two potatoes? Anyway, they kind of look like potatoes. But anyway, let's say these are all the people in California, and these are all the people in Washington. And now let's connect the members of the set if the two people know each other. Let's say we do that for everybody. So this person knows this person knows this person, and this person knows this person, and if this person knows this person knows that person, and if that person knows this person. Now, do you think this would be a function? Obviously, that is not a function. But if you have any kind of relation like this, you just connect any member to any member like this. This is what we call a relation. It's a relation. So all of these are relations. Two sets here, and we make a correspondence, a connection between the two members, if they are somehow related according to the rule. In this case, let's say we connect them if the person in California knows the person in Washington. Okay? And let's say people who live in California versus the people who live in Washington. We have to define this well, and then we make a connection. This one one person in California may know a lot of people in Washington, and of course the other way too. And some people in Washington know a lot of people in California. So we have all kinds of matches here. That would be a relation. But a function is a rule. A function is a relationship when each element in one set makes a one-way correspondence to a unique element in the other set. So exactly one element B. That's the key. If you have that, then this is called a function. In fact, that's the difference between a function and relation. So that is a function. Now let's look at, so therefore let me write down the answer here. The answer is this. So for example, 6 area rectangle to area. So this one a function, yes. This one was yes. And then now example 7. We have from what the r plus the positive number to square. Example 7. Positive number to a rectangle whose area is x. So this one is no. Because given a positive real number, there are many rectangles with that area. So the answer is no. Now let's look at example 8. Example 8. R plus, a relation from r plus to square, where f of x is equal to what? Rectangle whose area is x. Okay, now that means if the input is a positive real number, so given a positive number, we match that to a square whose area is x. Would that be a function? Everybody, example 8. Is that a function?
Provided it is not infinite, then I would say yes.
What is infinite? This is a function?
Rectangle whose area is x.
Okay.
So it depends on what x is. Oh no, then it would be no, not a function, because x can be anything.
X must be anything. X can be any positive real number. Now, given any positive real number, is there one square whose area is that number x, or are there many squares with that area with area x? So let's say if I give you, let's say, f of 3, for example, f of, let's say, 3, the number is the input is a number in this case. So let's say input is 3, and now so what is f of 3? F of 3 must be a square, and that will be a square. What kind of square? What are the sides of the square? That will be square root of 3 by square root of 3. In this case, the output is actually is a square. It's not a number. It's a square. It's a geometric object. It's not a number. So in this case, f of 3 would be a square, which is square root of 3 by square root of 3. So that's only 1. So is that the only output possible for the input 3? Or is there any other output? Is that the only output for the number 3? Input, output. But is that the only output? That's the question. Is that the only output? Or is that one of the outputs? Only output?
It's,
Yes or no?
I'd say it's one of the outputs, because a rectangle doesn't have all even sides. It could also have 1 and 3.
Right. But if you look at example 8, look at the range here. The range is a set of squares. So here we don't have rectangles. We only have squares. See this guy right here? The
Yeah.
input is what?
I saw what you say. When in that particular question there, it said rectangle. That's what was throwing me off.
Right. So the question is the example 8, a relation from r plus, from the set of real numbers, set of positive real numbers, to the set of squares. Is that a function?
No.
No?
It is.
Then what other output can you have? So if the input is 3, then the output is a square, which is square root of 3 by square root of 3. So this is if you said no, that means there's another output. What other output can you have besides this? Is there any other output? In other words, is there any other square whose area is 3? Because in this case, the range is the set of squares. We don't consider rectangles, we only consider squares. So is there another square whose area is 3? Or is it the only square whose area is 3? Question is how many outputs? Do you have only one output for every input, or can you have many outputs for some inputs? In this case, no matter what this number is, there's only one square whose area is that number. So in this case, the answer in this case is what? Yes. It is a function. There is only one square which has that area. I don't know, does that make sense? Does that make sense?
Yes.
Okay, let me give you another example here. Since I run out of examples here, let me give you another example. How about this save, and then I'm going to clear all this. So what I'm going to do is I'm going to say this. How about this? Let me now say this example. So let's say A, let A is equal to let A equal to how about this? US states. Which is equal to what? Which is equal to California, I don't know, Oregon, Washington, then Arizona, and then there's about 50 states, right? So that's why I'm right, US states. The US states. And the US states, and then at the end I need to put a parenthesis there. Yeah, the US states. Okay, and then let A, how about this? Let A is equal to the US states. And then now let B is equal to US cities. US cities. US cities. So US cities, like what? US cities, yeah, we have LA, and then we have San Francisco, San Diego, Las Vegas, and we have what? The Seattle, and then we have Denver. Anyway, there's zillions of cities out there, right? How many cities are there in the U.S.?
Mm-hmm.
How many cities? There's zillions of cities, right? All the U.S. cities, not the world cities, but the cities in the U.S. Okay, all the cities. So these are all the cities here. Of course, Santa Monica is a city too. So now let's make a correspondence. So define a relation. Define relation F. F of is define relation from A to B. Define relation F from a function relation F from A to B. Where, and then now here I'm going to specify the rule. I'm going to say F of, and then the state, given a state, is equal to the capital city of that state. Capital city of that state. Not any capital, but the capital of that city of the state mentioned. So, for example, what is the capital of California? All of you, do you know the capital of California?
Sacramento.
Sacramento.
What? Is it Los Angeles? Okay, no, it's not Los Angeles. You're right. It is Sac. Is it Sac? Yeah, it is Sac. What's Sac? Okay, you know what? For those of you who don't know what Sac is, then we put Sacramento. We call it Sac, right? Sac. Sacramento. Okay. Now this function out here, is that a function? Do you think this is a function or not? Is F a function? F a function? How about let's go to something more difficult. How about Washington? Does anybody know what Washington capital is? Oh, this is a hard one. Does any of you know the capital city of Washington State? What is it? Olympia. You know what? It's not Seattle, okay? Is it Seattle? No, it's not Seattle. Yes, you're right. It's Olympia. Olympia is a tiny city. Okay? It's a tiny city. Well, no, not the tiny city, but it's much smaller than Seattle, right? And that's the capital. And that's the only capital we have. Okay? So that is only one output. How about F? A function of, let's say, North Carolina. NC is North Carolina. By the way, in the U.S., I've only lived in two states. The two states, of course, right now I'm living in California. The only other state where I used to live is North Carolina, so I know everything. everything about North Carolina. I lived there for a couple of years. So what is the capital of North Carolina? Does anybody know?
Raleigh?
Does anybody know the capital of North Carolina? What? Charlotte? No, not Charlotte.
Raleigh?
Raleigh, R-A-L-E-I-T-H.
Yeah, I think many of you have probably have a hard time spelling the word, right? Yes, and you are right. It is Raleigh. Yeah, it's not Charlotte. Charlotte is actually the largest city. It's not Greensboro. There are many cities out there, but anyway, capital is Raleigh. So anyway, for each state there's only one capital city, right? So now the question is this rule, this correspondence, this relation from state to the city. This is the rule. Is this a function? Is it a function or not function? So
Yes.
my question is it possible to have two outputs? That's my question. Or should there be only have one output?
I believe it is
Wow.
a function, even if it has more than one output.
No. If we have if one output, if there are more than one, or there are two or more outputs for any input, then that's not a function. So in order to be a function, for every input, there must be exactly one output, unless there is no output. If it's no output, that's kind of okay. But there can only be one output or no output. But if you have two outputs, then what? Then it's not a function anymore. Two or more outputs is not a function. One output is a function. If it's not defined, then we can kind of say it's a function, but then in that case, we have to kind of restrict the domain. But anyway, if one output, exactly one output for every input, then that's a function. If you have two or more outputs for any input, then that is not a function. But all of these are still relations. And the answer in this case, yes, is it a function? And the answer is yes. But now, let me now do this here. How about now create another function here? And then how about let's say this. Define relation G. So what is G? G from A to B. Same thing. G from A to B. From the same steps. And now this I'm going to define. G of state is equal to city. U.S. city is the city of 1 plus million, a million of population in the state. Let's say I'm going to define this. Question is this a function? Now, if I define a function g, is that a function? Let's say, so we have a g of a state. That means if the input is a state, so we can put any state, and then what's the output? The output will be a city in the state, which has more than 1 million population. So in this case, we can say, what is this? G of California. Could be LA. Okay, yeah. So California is in input. Now, is there any city in California which has more than 1 million population? Yeah, Los Angeles is more than 1 million population. So is that a function? So my question is is G a function? Function? Yes. But note that G of California. Is there any other city which has more than 1 million population?
San Diego. So it's not a function.
Yeah. So we have one other city which has more than 1 million population. And then I think we have definitely California. Then there's another city. San Francisco definitely has more than 1 million population. And then other cities, I'm not sure. Sacramento, there are other large cities too, but I'm not sure. But anyway, these guys, they have definitely more than 1 million population. How about a city like, how about this? How about our favorite state? Somebody's favorite state. I don't think it's my favorite state, but let's say how about Wyoming? So Wyoming. So let's say if the input is Wyoming, WY is Wyoming. If you don't know where Wyoming is, it doesn't matter. Okay, this one is one of the states. So if the Wyoming, sorry to the Wyoming people, but anyway, Wyoming here. If the input is Wyoming, then what is the city in Wyoming which has more than 1 million population? What is that? Does anybody know?
Is there one?
You're right. Actually, there is none. In fact, the population of the entire state of Wyoming is what? Is far less than 1 million. I don't know, it's about 500,000 or something. So there is nobody in Wyoming. The Wyoming capital is Cheyenne or Casper. Those are the large cities. But you know what? Nobody has more than 1 million. So this one, undefined. You don't have any. There is no city. Again, the population of the entire state of Wyoming is, I think, is less than 1 million population. So there's nobody here. So anyway, this one therefore is what? It's actually it's not. In this case, it's not a function. Actually, the Wyoming example, I don't think I should put in there because it's undefined. So if you so this is not really a good example. Anyway, the reason why this function is not a function, the reason why this is not a relation is because of California. The California obviously have many cities. Many cities which have more than 1 million population. This one is because of this guy. The answer is no. This guy is not a function. All right. So if one input, if there is two or more outputs, then it's not a function. All right. So there are many states with more than 1 million population. I'm sure that Texas has many. That Texas has a couple cities with more than 1 million population. So I think Dallas, Houston, and what else? I don't know. There might be some other cities, but anyway. There are other states. So if any state has more than 2 outputs, if any for any input there are 2 outputs or more, then that is not a function. For example, these examples, this is not a function. Whereas this guy here, from state to the capital city, that is a function. So this is a function? Function? Yes. This one function? Is G a function? No. ¿Entiende? Capiche?
Capiche.
Capiche, okay, all right. I think I need to learn more languages, right? Yeah. Anyway. So that is it. Claro? Is it clear? All right, so it is claro. Okay, it's clear, right? Okay, so now let me now go here, and now let me go scroll this down. And now in example 9, you know what? These are different ways of writing the same function. In example 9, I have given you a function, how to express the function. And these are the different ways of express the function. And basically, let me write, okay, annotate. So example 9, these are basically 4 different ways of writing a function. So first one, this one is a set notational function. Although in this class we don't write the set this way, but this one basically this is a function. This means that basically this 1, 2 means that if the input is 1, the output is 2. If the input is 2, output is 3. And if the input is 3, output is 4. If the input is 4, output is 5, and that's a function. And then by a diagram. By a diagram, same function. I can do this. So I can call this guy F. That is the relation. And this diagram, okay, so that means we have 1, 2, 3, 4. And then the target, that is the range, has numbers 2, 3, 4, 5. Yeah, this is really basic. I don't know. Am I boring you? I guess this is really boring, right? Maybe I should not be spending time here. Okay, I'll try to move on quickly. So that is a function. So if you express the function this way, this is the function by a diagram. That's what I mean by a diagram. And now the number 3, by a graph. How do you express the function by a graph? And the by graph, it's this: 1, 2, 3, 4, and then 1, 2, 3, 4, 5, and this one you can call this the x-axis and y-axis. So the point is what? And this is 1, 2, and so on. 1, 2, And then this is 1, 2, 3, 4. Yeah, 1, 2, 3, 4, and so on. This is 1, 2, 3, 4, 3, 4, and so 1, comma 2 is over here. Then 2, comma 3 is here. 3, comma 4 is here. Then 4, comma 5 is here. So this is the point 4, comma. The last one is 4, comma 5. This. So can you express the function this way? Yes, we can. If we express the function this way, that's the equation, that's the function expressed in a graph. That is a function written in a graph form. That's the function by a graph. So this is a function, that's a function, but these are different ways of writing the same function. And then, of course, the number 4, this is the most concise way. F of x equals x plus 1. Where the domain of f is equal to 1, 2, 3, 4, it's set. It's limited. This is what I call the limited domain. So f, number 4, f of x equals x plus 1, and where the domain of f is the set containing the numbers 1, 2, 3, 4. So that means x could be 1 or 2 or 3 or 4. And then what's the output? Output is x plus 1. We just add 1 to whatever the input is. And so this is the algebraic definition of function. So roughly these are 4 different ways of expressing a function. Of course, the most common way of expressing a function in our class will be number 4. Of course, sometimes we will graph things too. So this one, graph 2 as well. Okay? So they are the same function written in different forms. Okay, now example 10, function here, and then these are the what? Evaluating functions. Yeah, so this one we did it already, so we're not going to do this again, or should I do this? Okay, if f of x equals x squared, let me write this here. What is so now here, class? If this is f of x equals x squared, so when you see this f of x equals x squared, what this really means is it means that f of this is equal to this x squared. Okay, so this is f of x equals x squared, right? So when you see this f of x equals x squared, this is how you should understand. What that means is, okay, now let me put a double arrow. What this means is, this means f of whatever we put in here is equal to whatever we put in here squared. So what we want to do is, we want to, do you see this x here? And then we want to block this off. Well, so why don't I put a parenthesis around the x? And then the next thing I'll do is, I'm going to now erase the x. That's what it means. So when you write f of x equals x squared, what that really means is f of whatever we put in there for x is equal to whatever we put in there for x and then square. So therefore, if you put in minus x, then what do we put in? We put in minus. We can put in minus x here, then we can put in minus x here. But whenever you put in this minus x, no matter what you put in there, there must be a built-in parentheses. Now in this case, there's already a parenthesis here, so we don't need to put this. And then here is already a built-in parenthesis right here. It's built in. So in this case, let's say, what is f of x plus h? What is f of x plus h? F of x plus h is equal to x plus h squared. So here, this is what I'm trying to say. When you substitute minus x here, don't just plug in minus x. Substitute minus x with a parenthesis built in. When you have to substitute 2x plus 1, don't just put in 2x plus 1. What you want to do is substitute 2x plus 1 in parentheses. If the 2x and the 1 get separated in any way, that will be a mistake. So when you substitute 2x plus 1 with a built-in parentheses. That's how you plug in. When you put in x plus h, don't just put in x plus h. So for example, if you say f of x is equal to, and then f of x is equal to what? X plus h squared like this, then of course this will be a mistake. That will be a mistake. Wrong. If you say this is equal to x squared plus h, that's wrong too. If you say that this is equal to what? Is equal to f of x plus f of h, f of x and then plus h, f of x plus f of h, wrong. X, wrong. All of these are wrong, basically. Oh, what I meant by this was this one. What I meant by this was I meant f of x plus h. Sorry. Here I should have written this correctly. So you erase f of x. What I meant by this is f of x plus h. F of x plus h is equal to, is not x plus h squared, it is not x squared plus h, it is not f x plus f of h. So don't do any of these weird things. So you just replace x by x plus h. And when you make a substitution, replace x plus h in a parentheses. So whenever make a substitution, always use parentheses. All right? Okay, any questions on example 10? Okay. Now let's get into example 11 and 12 and 13 and 14 and 15. On these examples here, now I'm going to go through a topic called natural domain. What is a natural domain? Yeah, you know what? Here, actually, I didn't write the definition of the natural domain. I guess I didn't. Yes, but basically, it's this. So let me write it over here. Given any function, natural domain is the largest possible domain. A set of all. How about this? Domain is the set of all elements or numbers, basically all numbers in the domain, in the numbers, a set of all elements such that the output is a real number. So this is actually the key. You know what? In this case, instead of natural elements, let me just call them numbers. Because in this case, we are actually going to consider numbers only. Numbers. So given any function, what is a natural domain? Natural set is the set of all numbers such that numbers whose, let me put it this way, whose output is real numbers. Whose output is a real number. Whose output is a real number. The collection of such numbers, the collection of all the numbers in the domain, that is what we call the natural domain. So let me explain to you what that exactly means now. So what I'm saying is, okay, so here let me erase this. Let me erase all this. We don't need these guys here. So let me erase all this. And so let me this here. And now let's look at example 11 here. Okay, example 11. Okay, example 11, it says, what does it say? Example 11, let me write it here. Example 11, it says f of x is equal to 2x and then plus 1. So we want the largest possible domain. When it says natural numbers, when you say, so x is the domain, x is the input. So the question is, what values can we put in here? What numbers can x be such that such that f of x is a real number. What are all numbers x? What are all numbers x? So let me address the question a little bit different. What are all numbers x such that fx is a real number? So can you tell me what the value of x could be so that f of x is a real number? In other words, if you put a number and then the output is a number, is a real number, then that value x will be part of the domain. So what kind of numbers are this in this case? What can x be? In other words, what can x be without causing any trouble?
1.
Could be 1. But now the question is, what are all the numbers? Not just one number. Yeah, 1 is part of the natural domain. But then can it be other numbers? What are all the numbers? That's what the question is. 1 is a number which can be, yes, that is true. 1 is part of the natural domain. But can it be any other number? Yeah. So basically the question is, can x be any number? Or
Yes.
is there a number where x cannot be? That's the question really. So in this case, domain of the function f is equal to, can x be any number? Actually, the domain of f, x can be any number. So this is actually what? The set of real numbers. In this case, actually, x can be anything. It can be 1, it could be -1, it could be 0, 10, 20, 0.1, square root of 2. It can be any number. So there is no restriction. No matter what the number is, the output will always be a real number. It must be a real number. That's why, in this case, the domain is the set of real numbers. This is what we call the natural domain. So in this case, I don't know why don't I just call this the natural domain? Natural domain. So you know what? Maybe to clarify this, let me do this. Let me save this here and let me erase this. First, you know what? Let me just give you to clarify this. Let me give you one more example here. I think maybe the meaning is not clear. Okay, a little bit. So let me explain. Okay, so what I'm going to do is I'm going to erase all of this. I already took a screenshot. Oh, by the way, the screenshot for this class, it can be found under the modules home. If you go home, that is home page. Is it the home page? You will see the screenshots there. Well, you can actually go to the bottom of notes, the files, and you can also find screenshots there. Okay? Yeah, I'm sure that if you have any so anyway, all of you should find the notes somewhere. Okay, the screenshots that is. How about this? Example. Number 1. F of x equal to 2x plus 1. Dom f is equal to what? Is equal to 1 and 1 comma 2 comma 3 and comma 4. Yeah, I just gave you this example right here. So let me just give you an example. This is the first example. That function. Now, how about this? Number 2. Let's say f of x is equal to, I'm using the same name, is equal to 2x plus 1. You know what? How about if I do this? G of x. Let me use a different name. Even though it's the same function. Okay, well, similar. Plus 1. And then where the domain is, dom g. Domain of g is equal to what? Is equal to 1. Is equal to, how about 2, and then 2 and 6 and 7. How about number 3? Number 3, h of x is equal to 2x plus 1. Then where dom h is equal to z. Z is a set of integers. Then number 4, how about k? Let me know the name of the function k. This equals k equal to 2x plus 1. That's plus 1. Okay, let's consider all these functions right here. Let's consider function number 1, number 2, number 3, number 4. Now, when you look at these 4 functions here, their rules are exactly the same. f of x equals 2x plus 1. But in the first case, first function f of x equals 2x plus 1, but we have set the domain. The domain is set to be 1, 2, 3, 4. That means we are only going to consider for the value of x 1 and 2 and 3, 4. In other words, we are only allowing x to be 1 or 2 or 3 or 4. That's it. Again, x is only allowed to be 1 or 2 or 3 or 4. So is that a function? Yes, that is a function. We have a rule and we have a domain. So that is a function. Now let's look at number 2. Number 2, the rule, the function, the rule is g of x equals 2x plus 1. It's essentially the same as f. But in number 2, dom g is the set containing 2, 6, 7. That means in this case, we only allow x to be 2 and 6 and 7. So that's number 2. So it says almost the same function, but we have a different domain. So is that a different function? Yeah, that is a different function, although the rule is exactly the same. Now let's look at number 3. Number 3, h of x is equal to 2x plus 1, and the domain of h is defined to be z, which is a set of integers. Okay, so now we have a function 2. In this case, we are letting x to be any integer. And now here is number 4. K of x is equal to 2x plus 1, and the domain is not defined. In this case, domain is not defined. How about this? Not specified. It's not written. Domain is not specified here. So if the domain is not specified, then what is the domain? If the domain is not specified, then what is the domain? Then what is
all real numbers?
Yeah. So in this case, you're right. In this case, if the domain is not specified, by the way, you know what, in all your math classes, many times what they do is they just write the function and then they don't write the domain. It's very common that in math, we have a rule and then they don't specify the domain. Sometimes they have a domain written out, but many times they don't write the domain. So then what is the domain? If they do not specify the domain, so in this case, if the function does not specify the domain, then we assume natural domain. So what is a natural domain? Natural domain is the largest possible domain. Largest possible domain. This is the whole thing. Okay. So if the domain is not if the domain is not specified, then what do we do? We will take the largest possible domain, and that's what we call the natural domain. So you're right. If for example 4, if they write k of x equals 2x plus 1 and they don't give us the domain, then yes. In this case, what is this? For number 4, in number 4, so let me write for number 4, what is it? Dom k is actually, dom k is equal to the set of real numbers. Which is set of real numbers? Set of real numbers. And for every one of those real numbers, the output is defined. So therefore, basically, that's it. Okay, so you know what? So you might say that isn't that always the case? And the answer is no. How about if you look at example 12? Example 12. Example 12 here. We have example 12 with this guy right here. Oh, you know what, class? This is only 9:50. Is it time for break? Oh, I barely did section 1.1. Okay, you know what? I think it's time now. Before it gets later, I think why don't we take a break here? Okay, so we have 10-minute break. Continue at 10 a.m. All right. Right now it's 9 a.m. 9:50. So we will exactly start at 10 a.m. Okay. I will be back. Okay. Everybody will have a 10-minute break. I'll be back in 10 minutes. Okay. I'll be back in 10 minutes. We'll meet at 10 a.m.